Today we're going to look at what makes your electric motor spin. Now, electric motors are an extremely important thing to us. I could probably reasonably say that the first use of magnetism was making a compass, so people could find their direction, sail across the seas, explore, and all those things made the world just grow enormously because of exploration and stuff. People were no longer confined to like a small location where they could just walk from, one end of the village to the other end of the village. They could use things to navigate from one place to another. I would probably be correct in saying, although I do not know this for sure, but the electric motor was probably the second major invention using magnetic field. And electric motors have just changed the world ginormously because in the Industrial Revolution, we had to have either water wheels to run machinery or steam engines to run machinery. The electric motor replaced all of that. And electric motors are everywhere in our common life today. You might not even think of it, but your refrigerator has a compressor in it run by an electric motor, has fans that run by electric motor, your heat, the electric windows on your car, right? And so anything that moves, essentially, is probably operated by an electric motor. Here's a short video describing how to make the motor that we want to use for this lab.
Begin by wrapping 20 gauge magnet wire around a D battery until you have about 10 coils. Now take the ends of the wire and wrap them around the coil until they hold it securely in place. Make sure both wires are directly opposite of each other on the coil. With the coil standing vertically, sand the top half of the insulation off both wires. Now take two paper clips and bend them into long hooks with loops of wire at the end. After that, use electrical tape to secure the two paper clips to the D battery. Make sure that the loops of wire are about the same height off the battery. Now you're ready to put your electric motor together. Start with the base of either clay or Play-Doh. Place the D battery securely in the center with the loops of wire facing upwards. Now place a neodymium magnet on the top of the D battery. Finally, you're ready for your coil of wire. The coil of wire is an electromagnet, and when connected, it will begin to line up its magnetic fields with that of the neodymium magnet. However, since only half of the insulation was removed, as the electromagnet rotates, it turns off, gliding through the second half of the turn, only to repeat the process. If the insulation is removed from both sides of the wire, the electromagnet will turn to face the neodymium magnet, but then stop once both of the magnetic fields are lined up. Thanks for watching Bearded Science Guy. If you enjoyed this video, hit subscribe or check out some of our other weekly science videos.
So today we want to look at what makes our electric motor rotate. So to do so, I'm first going to just start with this cutaway of an electric motor that's just quite a bit more complicated than what we have, but it still has the same basic parts. All right, so all motors operate the same way. Is we have a magnetic field, and then in that magnetic field, we have a coil that has a current in it. So we know that a coil with a current in it will experience a force. And that force causes the motor to rotate. So let's look at this motor. Well, right here, we have this coil. So this is a big electromagnet here, a big electromagnet down here, and then this is our coil. So our magnetic field is going to run this through here. Okay? So this coil is called an armature. Right? That's an important word you should know, armature. So that's our basic parts of the motor. So something that makes a magnetic field, in this case an electromagnet, a coil, in lab questions we have a magnet. All right, well, we know magnets, that's a permanent magnet, so we'll use one of the permanent magnets in the classroom. We could use an electromagnet if we wanted to, but we can use the permanent magnet, and we know that field flows out of a magnet from north to south. So we have essentially, I'm not going to show it curling all the way around, but essentially we have field flowing out of the magnet from its top. So we've made the, now after you've made the coil, we sanded half of it off on these ends. This is made out of enameled wire. What enameled wire is a wire with a very thin coat of spray paint on it. And so what that paint does is it insulates it, because if we had all of these loops all touching, we wouldn't have a motor anymore, we wouldn't have a coil anymore. That's any use to us because it would all short circuit and it would just not work, just heat up and be a mess. All right, so we have our coil made of enameled wire. Well, for the coil to make contact with the battery, we have to sand some of the enamel off where we're going to make contact. We put our coil on the supports, all right, and then let's look at the forces on the coil. So we know our magnetic field is going from north to south. So our current is going to come from the battery and go this way around, all right? And so let's look at what happens. So we have field going up and down, or just going up, all right? We have current going to the left. So how would we find that force? We would point our fingers of our right hand toward the top of the page, point your thumb toward the left, and you'll see that your palm is facing into the page. All right, so your palm is facing away from you. All right. So what do we have to do when the current gets all the way around to here? Now it shows it coming out here, but what it does is we know that it loops around and around and around and around and then goes out back to the battery. All right, so if we have force going this way, the only thing we have to do is keep your fingers pointing straight up and rotate your hand around till your thumb is now pointing to the right. Your palm should be facing you, and that gives us a force that is coming toward you. Now, if we suspend an item, all right, from these endpoints, this loop, all right, so it's suspended on the paper clips, and we apply a force at A coming toward you, and apply a force at B going away from you, this object should rotate, and which indeed it will. We saw that already in the little video on the motor. So here's our motor before it begins to rotate. When it rotates 180 degrees around, well, we notice that A is now on the bottom. All right. B is now on the top. So our current on the bottom is going to the left, and our current on the top is going to the right. So if we look at our forces, the forces flip. So now if I'm pushing at A and pulling at B, the motor rotates back around the other way. We can't have this, all right, because our motor, if we could get it to go around, is going to be very, very inefficient, because it's going to be forced one way, then the other way, then one way, then the other way, just back and forth, back and forth. Sometimes I've made these where I get it to just go back and forth, back and forth, back and forth, and it never actually rotates. So we want our motor to keep rotating by its own. Well, what would keep something in motion? We call that inertia. So we want the motor to keep rotating, all right, around and around. So what we've done is, in the first part, we've sanded underneath here to get rid of the enamel so we get current to flow. Well, now the sanded part is up here, all right? So once the sanded part is up at the top, there's no more contact. So what we can do is, if there's no more contact, there's no more current, so there's no more flow. If there's no more flow, there's no more force. So the force just shuts off until what happens? it goes another 180 degrees and we're right back to where we started. So what it does is it pushes halfway around, turns off, its inertia keeps it moving till it gets back to here, and it gets another push, turns off, gets another push, turns off, gets another push, and turns off. That's how motors actually cause things to keep going around and around and around. This dualism of turning on, turning off, turning on, turning off. Now here's an example of a slightly more sophisticated motor that's doing the same thing. We have a bar magnet, all right, that's creating magnetic field. I would say based on the direction of the forces, I know that this would be the north and this would be the south, and I'd have magnetic field flowing from here to here. A horseshoe magnet is nothing more than a bar magnet bent into a curve. So let's take a look at how this motor operates. This is very similar to yours. So we have current coming in. It hits this thing, which makes current go that way and a force that way. Again, current's going this way and a force that way, so it's going to spin this way around. Well, our motor, we had to shut it off every 180 degrees and let it rotate back down around to its original position so that it could rotate again. Well, this motor just has a different device. What happens with this thing, this motor has what we call a commutator. This commutator, you don't need to know that, but it's just a little interesting fact. This commutator switches the current, all right? So the armature goes around once, and then instead of being forced backwards or the current shut off, the current reverses to go this way and that way. And so then it gets pushed another 180 degrees. So this would be like a two-stage motor, all right? We have forces applied to it every 180 degrees.